You may remember about 2 years ago, almost every retro channel that was into the Amiga covered something called the PIStorm, a way to accelerate your Amiga using a Raspberry Pi. And because I'm basically allergic to all the advice that YouTube gives you on how to make a successful YouTube channel, I've waited 2 whole years to now make a video about it. Take that, YouTube algorithm. Now, most of the videos you've seen on the PIStorm probably fall into these 2 categories. Someone fits one and shows you how to set it up. Someone's already set one up and would like to show you how fast it is. And while I am going to do some of those things in this video, I am also going to go into this in extraordinarily nerdy detail because this is Retro Bytes. And apparently I can't go for a topic without giving you its full backstory and also digging into a whole bunch of its technical details on how it actually works. I'm really hoping this is why you subscribed. So in order to look at the history of this sort of thing, I'm going to start with history's greatest 8-bit micro, Acorn's BBC. Yes, I may have borrowed and slightly modified a phrase there. Now you may be wondering why a video about an accelerator for the Amiga is starting with the BBC Micro. Well, hopefully you'll see by the end of this. One of the least known about features of the BBC Micro is a port called the Tube port, which allows you to add a second processor to the BBC Micro. When you've got a processor connected up this way, the software runs on that second processor, and the processor built into the BBC, the 6502, works as an I/O processor. And Acorn released quite a variety of these second CPUs. You could get a second, faster 6502, which also meant that your processor had access to all 64K that it could address as RAM, and didn't have to use any of that address space for ROM or video. There was a Z80, so you could run CPM. There was a National Semiconductors 32016, so you could run Panos. I mean, God knows why you'd want to, but yeah, you could. And of course, the first ARM processor was available as a second processor for the BBC. In fact, that was the only way it was available to start with. And you even had 186 and 286 second processors, so you could pretend to be a PC. Now, with all this software kicking around for the BBC for extra processors, it's not that surprising that BBC collectors really wanted to try this stuff. The problem is, for a lot of these second processors, not many of them were sold, and even less of them had survived. So, they were becoming more expensive and harder to find. Now, the Acorn community seems to be incredibly resourceful when it comes to creating new hardware for the machine and software. So, unsurprisingly, they started making new second processors, and we got to see 6502-based ones and the odd ARM-based one coming out built using, actual processors. But then, some bright spark thought, I know, I can stick all of these CPUs and get the Tube ULA all into an FPGA, and then we could have one little Matchbox processor that does all of the CPUs, and unsurprisingly he called it the Matchbox processor. And at the time when he was showing it off in Wakefield, I was heartily impressed. I've never seen Tube Elite go that fast before. The only problem being, though, it was not the easiest thing to make, and also not the cheapest, because FPGAs, they keep going up in price, and occasionally your FPGA that you've done your design on, someone will just stop making the darn thing. And this is where we get another bright spark who thought, I know, I'm pretty sure the Pi can emulate all these CPUs at a pretty decent speed, and they keep making those. Hence we get the idea for PiTube Direct, a second processor add-on for the BBC Micro that can do all the processors that were ever made for it, and a few more. And in fact it used the same StarFX commands that the Matchbox CoPro used to change between processors. So how did this all work? Well, the Tube port has a protocol it uses to talk to all the second CPU add-ons, and there are not a lot of signal pins involved in that, and it only runs at about 2 MHz. So this falls within the sort of frequency that the Pi could actually do in terms of I/O out of its GPIO pins, and on the BBC side we don't have more signal pins on the Tube port than we have GPIO pins on the Pi. So this feels like it's a fairly simple case of being able to just wire up a GPIO pin to a corresponding pin on the Tube port and just write a little bit of software. Okay, there's way more to it than just write a little bit of software, but we'll cycle back to that one. Now there is one little wrinkle here. Modern electronics tends to use 3-volt logic, whereas more retro machines from the 80s use 5-volt logic. And this is true for the Pi and the BBC. So we do need a little PCB knocking up with some ICs that just shift between 5-volt and 3-volt logic. Speaking of PCBs, we should probably have a quick word from the channel sponsor, shouldn't we? Yes, today's video is sponsored by PCBWay, fine purveyor of CNC services and 3D printing, and they also make, wait for it, printed circuit boards. You knew that name had a reason. If you have something you're prototyping or want to do small runs of, well then PCBWay are there to make your cases, boxes, gears, 3D print your stuff, make your PCBs, even put the components on for you if you want. So we've got our fairly simple PiTube Direct board. One connector to plug into the BBC, one connector to stick into the Pi, and a bunch of level shifters in the middle. Which of course leaves all the complexity to the software. Now, for all the various processors they were going to emulate on there, and there's a lot, in fact, here is a list on the screen, people working on the PiTube Direct were not going to write all the CPU emulators themselves. And that's because they already existed and they were open source, and they were planning on making this open source too, so why reinvent the wheel? Where the complexity comes in is not getting all those CPUs emulated themselves, but it's in doing the software layer that allows PiTube Direct to speak the tube protocol, and also map all the bits of memory and the tube ROM and other address space bits around each CPU implementation. Now, doing all of this and getting it running fast enough on a Pi Zero, bit of a challenge. And one of the reasons they wanted to also hit the Pi Zero was so that it could just fit in the little trapdoor slot underneath the BBC without having to have some kind of ribbon cable poking out from under there. Now, in order to hit that performance point, they were going to have to do something a little bit special. They wouldn't just be able to run the PiTube software under Linux or another operating system running on the Pi. They need to take it over completely. And this is where we introduce something known as Bare Metal Pi. Bare Metal Pi is a series of libraries that lets you hit the hardware in the Pi directly. You don't need an operating system. You can use this to compile a binary that can be run in place of a bootloader that just starts running your application, hitting the hardware directly, and no operating system to get in your way. Essentially, your code gets loaded in the same way that the Linux kernel does when it boots. Now, this gives you the advantage that you are completely in charge of the hardware. You can make the DMA controller do whatever you want with the pins, you're in charge of all the interrupts. The disadvantage of this is that you're in charge of all the interrupts, the DMA control and memory allocation, you know, the whole shooting match. It's kind of a two-edged sword. You can squeeze a lot of performance out of things doing this way, but there's also kind of a lot of work involved. Your codebase is responsible for everything. Now, luckily this is where the Bare Metal Pi libraries helps out, as that library provides something that looks more or less like the standard C library, so you can write application code, but when it's going into file, etc., it's actually using part of the Bare Metal Pi library that has the code in it that's capable of, reading and writing from the SD card and dealing with a filing system. It's kind of like you're compiling your operating system into your application, but doing it this way certainly adds a degree of complexity to doing stuff. Now, you may be wondering why I'm telling you about all this Bare Metal Pi stuff. Don't worry, it is going to be relevant to our PIStorm any moment now. And this feels like a pretty good time to jump to talking about the PIStorm itself. Now, PiTube Direct was getting fairly well known about, and a number of people thought, well, maybe we could take this sort of approach and do it for the Amiga. Now, the Amiga had no shortage of accelerators. Back in the day, lots of people made different accelerators for the Amiga, lots of different companies. The only problem being that they were quite expensive then, and, well, they certainly ain't getting cheaper now. So people have come along to create new accelerators with the aim of having accelerators be much more available for the Amiga and cost less. The problem is, for some projects, cost less still didn't necessarily mean affordable for the vast majority of Amiga owners. Some had started off trying to be affordable, but unfortunately with the constant ever ratcheting up of the price of FPGAs, and the fact that that was the core component of their accelerator, meant the price of their accelerators kept ratcheting up. So you can soon see what the appeal was of this cheap second processor for the BBC. The whole point of the Pi is it's supposed to be affordable, that's why they exist. But if you wanted to do this for the Amiga, it's not quite going to be as simple as it was for the BBC Micro. Now, in some ways, the people aiming for the Beeb had life a little bit easier because they had the tube port, a dedicated port designed to add an extra processor for you. And that extra processor did not replace the processor on board, it's in addition to. With an Amiga accelerator, the onboard processor is disabled, and the processor that you add on is going to be the only processor in the system. Which means that CPU has to deal with everything the onboard one used to deal with as well. All the interrupts, any memory access, to chips built into the Amiga itself, that's all got to be done by the processor that you're adding in. So there's more that the accelerator is going to have to do than PiTube Direct had to deal with. So this means our PIStorm board is going to have to essentially deal with every single CPU signal and provide to the system all the functions that the original 68000 did. And the 68000 is a 16-bit chip, so you've got 16 data pins to deal with. It also has 24-bit memory addressing, so there's a whole bunch more pins you have to cope with. Then you have to deal with the other signals the CPU has to cope with. such as halt or interrupt. Now all told, the original 68000 came in a 64-pin package. And there's something you might note about the header on the Raspberry Pi that's used to connect stuff. It's got 40 pins. 64 pins does not fit into 40 pins. And out of those 40 pins, quite a few of them are reserved for things like power or I2C. So we can't even just use all the pins that are on the header. So we're going to have to do something a little bit more complex and a little bit more clever with the board that links the Pi to the interface with the Amiga. And this is why PIStorm boards tend to cost a bit more than their PiTube Direct equivalent, because there's more components on there. Not only do we have all these level shifters used to go from 5V to 3V, but we also need a chip to contain the glue logic that gets us from all the pins and signals we need to deal with to pretend to be a 68000 to the machine we're plugged into, and the few pins that we're allowed to use on the Raspberry Pi. This is why the PIStorm has a CPLD, a complex programmable logic device. This chip is kind of a bit like an FPGA, but with a lot less gates in it, and importantly in a much lower price point. The other big difference of a CPLD is whatever configuration of gates you want in your CPLD, that's flashed into it, and it remembers that, so on power up it works straight away. An FPGA needs some form of external store with its configuration in that it pulls in after it powers up. And this difference makes it quite a nice choice for implementing a low-cost accelerator, because firstly, it's cheaper to start with, secondly, it doesn't require any additional chips to get itself out of bed, and also, we kind of need it to do something the moment it's powered up. Once you've decided you're going down the CPLD route, someone has to do the VHDL design so that the CPLD actually does something. And there's two parts to that design. There's the bit that actually interacts with all the 64 pins that are the interface that's pretending to be the 68000, and the next part is doing the protocol that talks between it and the Raspberry Pi so the two can communicate, so the Pi can essentially do all the work of being a 68000, or at least pretending to be a 68000 where it counts. So once that protocol is designed and your VHDL is done, you still need the software that's running on the Raspberry Pi side of things. Now this is initially where PIStorm took a bit of a different approach from the PiTube Direct people, in that they decided that theirs would be a user space application running under Linux on the Raspberry Pi. I know some of you who have been following PIStorm all the way through will now be at the edge of your seat screaming something about a certain other approach. We will come to that, do not worry, we're doing this in chronological order. Now, one of the advantages of doing this whole user space program under Linux thing is that you've got, well, the whole of Linux there to do all your operating system and file type functions for you. It's a lot quicker to go from I have an idea for this thing to getting it implemented if you don't have to worry about everything that's not just the bit you want to write. It's even quicker if there's lots of implementations of CPU emulators for various Motorola 68000 series CPUs as well. So essentially, once you've got your VHDL and you're doing a user space application, you can take an existing 68000 implementation, implement your protocol between Pi and the CPLD, and before too long you've got yourself a minimal working implementation that you can start to do some stuff with. But the problem with this minimal version is that, well, it doesn't really get you very much. What you've got is now a 68000 implemented on your Pi, and your Amiga's no faster than it was to begin with, and that's because there's a limitation with how quick you can ship data in and out of the Amiga. You see, that CPU, the original one, was clocked at about 7 MHz, and it's still clocked at 7 MHz. That way, in and out of the Amiga circuitry, it doesn't go any faster just because you've stuck a Raspberry Pi on it. And this is true of all the original hardware accelerators for the Amiga. You might be able to get a 68030 with enough chips surrounding it to pretend to be a 68000, but it isn't going to make your Amiga faster just because that's there. It's still clocked at 7 MHz, it's talking to its memory at 7 MHz, and with chip RAM, it's talking to its memory at 7 MHz when the chips want to let it. So it's kind of talking about half that speed most of the time. For our accelerator to be of any use, it needs its own memory. And luckily with the Raspberry Pi, that's pretty easy. You can just use some of the Pi's RAM, map it into your emulated CPU, and you've got more RAM, right? Well, it's a little bit more complicated than that. First of all, you have to map it somewhere into your address space. Now, if you're being a straight 68000, you've got 24-bit memory addressing, which does not equal a lot of memory. But if you're pretending to be a 68030 or 020 or 40, well, then you've got 32-bit memory addressing, and that is a much larger memory address space to put your new emulated RAM in. The problem is, just because your new virtual CPU can address more memory and has access to more emulated memory, doesn't mean it's going to use that memory. The problem is, the original operating system boots off the Kickstart ROMs built into your Amiga, and it knows about a very limited amount of memory to start with that it can assume is there in all Amigas. As the operating system loads, it needs some way to configure extra memory into the operating system so the operating system knows to use it and start placing application code there. In fact, we need the operating system to use that memory in preference over the chip RAM and any FastRom that's in the Amiga already. Because if it doesn't, then accessing that memory has to happen across that 7 MHz divide between our Pi and the original Amiga hardware, which is the slowest way that our emulated CPU is going to access stuff. We really want it to be using the memory that's inside the Raspberry Pi, because it can access that RAM a hell of a lot quicker than it can access the RAM inside the Amiga. I mean, even with the original accelerator hardware that was available back in the day, that's what the system did. Your 68030, for example, would try and use the memory that was on the accelerator board in preference, because it could access that at the full clock rate that it was clocked at, and didn't have to cross that 7 MHz clock domain back into the original Amiga hardware. And with our emulated CPU, it's no different. We want to be able to use that internal Pi memory, so our emulated 68K replacement can run as fast as it possibly can, before it eventually has to access or send something over that 7 MHz clock divide. So in order for this memory to be detected, the Kickstart ROM has to initially take charge of the machine and detect all devices and any ROMs contained within them, and memory expansions as well. Once it's loaded the device drivers from any ROMs, built the device map and memory map, it then runs the strap part of Kickstart that actually boots the OS or whatever games you're going to run up. Now, not all RAM is detected in that initial Kickstart phase. Some is added once the Amiga's operating system is booted. Now, with Amiga OS, you have a kernel called exec, and exec maintains the list of blocks of memory it can use to allocate things from. It does that as a simple linked list. And that initial linked list is generated from the list that Kickstart initially produces. Luckily though, exec provides us with a function that allows us to add another block of memory to that linked list. The function is called addMemList, unsurprisingly. And when you call that function, you tell it how much memory the size of the block is. That's then followed by telling it the type of memory it is, for example, FastRom. The next argument is the priority that memory has, which is the extremely useful bit for our accelerator, because we can give it a higher priority, tell it it's fast memory, and therefore the kernel will allocate memory that's going to applications for executable code and data from that block of memory first. Then finally we tell it the address that the block of memory starts at, and then we can pass it a string so it can be identified when something wants to list out the different blocks of memory that are available, like sysinfo for example. So this has got us our basic working minimal accelerator. We've managed to get an emulated CPU that's faster than the original 68000. We've got some memory in there, so now the code actually runs on the Pi side of things, which makes it a lot faster because it's no longer crossing that clock domain divide between the emulated machine and the actual Amiga hardware. But typically we'd like to get a few more things out of it than just that, and PIStorm delivers on that front. We're also able to create some virtual devices and have those addressable by the CPU, again, on the right side of this divide from a performance point of view. Now, one of the big things people wanted in their Amiga back in the day was RTG, retargetable graphics. Yes, we could have fancy high-resolution screens with higher colour counts and chunky pixel mode rather than planar pixel mode, which is great for first-person shooters and other 3D games. And PIStorm provides that using the GPU of the Pi to back it, and uses the HDMI output from the Pi in order to display it. And because that RTG device is on the Pi side of the communications bottleneck, we actually get to access that as a decent speed from the emulated CPU. Another device we can provide is hard disk emulation. We can access a file stored on the Pi storage and hand that out to the Amiga as if it's a hard drive. And again, it's on the right side of that bottleneck. Now, the other virtual device that the original version of PiStorm's been working on letting us have is that of an emulated Ethernet card, so we can do TCP/IP from our machine. I must admit, that's not the easiest thing in the world to set up, but it does work. It's experimental, but it does work. Now, speaking of this bottleneck and clock divide, this was obviously a problem for original hardware Amiga accelerators, and they did a very similar trick to what we've been doing with the Pi and the PiStorm. in that while initially we got accelerators that were just RAM and a CPU on a card, quite a lot of the accelerator vendors did start to make things like graphics daughter boards you could add onto the card, so you could have the RTG on the right side of the bottleneck. SCSI controllers were also an option for quite a few of the accelerator cards as well. So it's not like this is a modern thing or got anything really to do with the Pi itself, although there is a limit to how fast you can make the little pins on the Pi go. It's all about solving a problem that's always been there for accelerators, and they're basically solving it in the same way. As a little hardware example, here's the B-Vision add-on for the CyberStorm accelerator cards for the Amiga 1200. This thing was essentially an RTG card with some 3D acceleration in it that you could add to your machine and, well, run some pretty high-end games for the Amiga of that time, including my favourite, Wipeout. Now, so far, we've talked about getting the CyberStorm up to the point where it's running on top of Linux and able to talk to 16-bit Amigas. Now, that isn't where things have ended. We've actually moved a bit beyond that now. But before we get into all of that, let's have a little look at a PIStorm itself, and I'm going to fit one inside my Amiga 600. Now, the poor Amiga 600 probably is the, well, least regarded of the Amiga machines that were half popular. The problem is, Commodore originally intended this machine as a low-cost Amiga, one that would replace the A500 and A500 Plus, sit somewhere in the market where the Commodore 64 had been for quite a number of years, and hit that kind of price point. The only problem was, Commodore being Commodore somehow managed to design this thing in such a way that it cost them more money to make it than it cost them to make the A500. So suddenly their low-cost entry point machine is now actually not that low cost at all, and somehow Commodore's marketing department has to make this thing seem like an upgrade over the A500. So they call it the A600 instead of the A300, and then as far as I can tell, largely BS from there on out. It's not that I have anything against the A600, I actually think it's quite a nice little machine. The smaller form factor, yeah, pretty good. An onboard IDE controller, actually that was quite an improvement over where we were with the A500. We didn't have to buy an add-on in order to get a hard drive controller. But it was missing a number pad, which annoyed the hell out of anyone who liked flight simulators or any other kind of game that used a number pad. It had exactly the same graphics chipset as the 500 Plus, and the same kickstart. But by and large, Commodore had removed all the expansion possibility by getting rid of the side slot that most A500 users used to upgrade their machine when they wanted to add something a bit more powerful to it, and gave us a PCMCIA slot. Now, Commodore thought that slot would somehow make hardware upgrades cheaper for the A600. You could add peripherals that were intended for the PC, which were on average a little bit cheaper. The reality was, though, Amiga owners ended up still paying more for their add-ons, even though the hardware was effectively a rebadged card aimed at a PC, but with a driver finally written for the Amiga and a bit of a change of the firmware on the card. To make matters worse, it's that PCMCIA slot that pushed up the cost of the A600, meaning that it had to be called the A600 and not the A300. And if you're an Amiga owner who wanted an accelerator, well, none of the ones for the A500 were going to work. And there wasn't anywhere to put one because, no side slot. And the A600 was also constructed using surface mount rather than through-hole, which means we couldn't take the CPU out, like we do with the A500 when we stick in a PiStorm. No, it has to sort of vampire over the top of the chip that's surface mounted to the board, where all of these little pins dig into all the signals heading into the onboard chip. In fact, a certain line of FPGA-based accelerator that started with the A600 takes its name from this whole vampiring into the chip. So once we got the thing fitted, we can power our A600 up. Now, the onboard 68000 is effectively inhibited, which stops it from doing all the system functions it would normally get. So our system's held for a few seconds while the Pi gets booted up, and in this particular case, runs the kickstart from the original A600. Now, the kickstart can be remapped so that the kickstart, instead of using the ROM on board, essentially uses a ROM on the Pi side of thing, and that a ROM file gets loaded up into memory, and the kickstart starts executing from there. Now, that gives us two advantages. Firstly, that it's a lot easier to upgrade our kickstart ROM. We don't have to open the machine up, lever out ROM chips, actually get ROM chips burnt for us and put them in the machine. But the main advantage of remapping the kickstart ROM into the accelerator, and again, hardware accelerators back in the day did this, it means that the kickstart RAM's now on the right side of the bottleneck, that is where the 68000 joins the Amiga circuit board. So that means all the operating system calls that we make to libraries that are stored in the kickstart ROM now live on the fast side of the Amiga in the Pi. And yeah, there were quite a lot of calls, particularly for applications, to these libraries that live in the Kickstart ROM. So it gives us a reasonable performance boost. Of course, makes no difference to games whatsoever, because hardly any of them used anything that was in the Kickstart ROM once they got loaded. Now, so far we've talked about PiStorm in just its 16-bit variant, and also assuming that we're booting Linux on the Pi and then running a user space application that pretends to be the Amiga accelerator. And that was the state of PiStorm a couple of years ago, but the state of PiStorm has moved on a little bit. We now have PiStorm 32 for a start. The original PiStorm targeted the 16-bit Amigas, your A500, your A2000, and a bit later on the A600. But once we start getting into the later bigger box Amigas, like the 3000 and the 4000, and your A1200s, well, we started to work on a minimum of a 68020, which is a 32-bit CPU. So we have 32-bit addressing, and we have 32-bit data access as well. Now, the PiStorm 32 is aimed at the Amiga 1200, and it doesn't work by removing the original CPU, because again, it's surface mount, and also with all those extra pins, you can imagine trying to vampire around that thing, but fortunately we don't have to, because the Amiga 1200 brings all the signals we need to the slot connector. Now on the 1200, the slot connectors is underneath the trapdoor on the bottom of the machine, so this makes fitting the accelerator a lot easier. But with 32 data pins and 32 addressing pins, plus the other pins that you need, this makes the job of going through the few pins we have available to communicate with the Pi, and all the pins we have to communicate back with the Amiga on, a lot harder. So this is one of the reasons why the PiStorm 32 costs a bit more than the original PiStorm, because we've got an FPGA on there rather than the CPLD. This means we can have a little bit more complicated logic in there, but importantly we have more pins on this chip than we do on the CPLD, so we have enough pins that we can talk to all the pins we need to talk to on the slot connector for the A1200. So that was being the big change on the hardware side of things. We now have the PiStorm 32. But the software side of things hasn't stood still either. Now, I've talked about it all running on top of Linux up until this point, and, well, now we have EMU68, which works a lot more like PiTube in that it doesn't run on top of Linux. This stuff hits the Pi hardware directly. It also uses a just-in-time compiler rather than more traditional emulation techniques for the 68000 side of things. Now, this approach has given us a couple of advantages. We get a little bit more performance out of our Pi hardware because we don't have an operating system in the way, and also we have the JIT. However, it does make emulating some of the other bits of hardware a bit more complex, particularly the hard drive. When we had the version that was resident on top of Linux, well, we could just use a hard disk file on one of Linux's many filing systems that it supports. And the application doing the work of being the Amiga didn't really have to know how to, write a filing system or anything. It could just put bytes in that hard disk file and have the Linux kernel take care of getting that into a file on a filing system. Once you don't have Linux, well, life's a bit more complicated. So EMU68 takes this approach where any partitions on the SD card it booted from that happen to have an ID of 76 in hex get presented to the Amiga as a hard disk. Now, this saves a lot of code on EMU68 side of things because it doesn't have to understand the filing system or anything like that. It can essentially just read in the partition table, look for the beginning and the length of the partition, and there you go, it presents a block device that has the same length as that of the partition and just has to essentially remap what it reads in from the Amiga side of things to a location on the disk. The other advantage of this approach is we don't have to wait for Linux's kernel to boot and all the daemons that you're running on that particular Pi. And while EMU68 does also take some time to load and start, it's nowhere near as much time. Which, given that we're used to an Amiga just being a machine we power on and it goes, yeah, that's quite handy. There are also some disadvantages. We don't really have a network card device anymore, and while not impossible for EMU68 to implement at some point in time, it is a lot more complicated for them because they don't already have a whole networking stack, NAT. And importantly, all the wireless support, including the WPA supplicant, necessary to make joining the wireless and working a reality. So it means they'd have to recreate a lot of that code or at least find a decent way of porting it, which non-trivial. But for the purposes of our little A600, I'm just going to stick a PCMCIA network adapter in the side and plug it into Ethernet. It won't be rapid, but it will allow me to easily copy software from somewhere else to the Amiga. And that does bring me to another little advantage that the Linux-based version of this had, and that there was a full Linux system running on the Pi, so you could just SSH into it, and you could copy a hard disk file back and forth, load it up in an emulator on your bigger machine, put files in, copy the whole hard disk file back. And of all the things I'm going to miss by moving to MU68, yeah, that's going to be the one. Well, if you got all the way to this point, I'd like to say thank you very much for watching. I hope you've enjoyed our tour as to how these things actually worked and why they came about in the first place. And if you did, YouTube's given you a little button that's there to indicate that fact. It's especially there for the purpose. And as ever, it'd be nice to chat to you in the comment section if that's something you feel like doing. And if you'd really like to help the channel out, why not hit that subscribe button? Because honestly, it does make a big difference to whether YouTube can be bothered showing this video, to people who are using YouTube.